Welcome all to another session of TIFR Math problem solving. Today's question is pretty straightforward. If you know about the Gauss's theorem regarding when the group of units are cyclic, so he kind of classified that entire section. Okay. So for this, you need to have an understanding on the direct product of groups. So direct product of groups and Chinese remainder theorem. And the Gauss's theorem. Okay, so basically you need the Chinese remainder theorem to prove the Gauss's theorem. Now in this session we will not be proving the entire Gauss's theorem, but we will see that how understanding Gauss's theorem gives us the entire solution. So there are some side notes that you might want to study first and before solving this type of problems as well. Those concepts are fundamental theorem of finite abelian groups and some properties of UN. So basically that is the group of unit in this setup that we are actually taking. So let's say basic properties of group of units. Now Gauss's theorem tells us this. So it tells us that the group of units, that is UN, is cyclic if and only n is equals to 1, 2, 4, p to the power k or 2p to the power k, where p is an odd prime. So UN, the group of units. So generally you might have seen it like this as well, like for Zn cross. So this is also one of the ways to make sure that what are the groups of units are. Okay. So if we have this UN is cyclic, and this is one of the notations that we use for UN, that is Zn cross, G cross, I mean the number of co-primes. Okay, so the number of co-primes under multiplication is it forms a group. So hence, because of this Gauss's theorem, as you can see that in this problem, it automatically becomes false. So there exists an integer such that the group of units is cyclic. So what is here? It is, as you can see, that this only holds. This only holds when this pk to p to the power k and p is an odd prime. Okay, so this only holds for when we have p as an odd prime. All right, but here, as you can see, that we have 2 to the power n. So here, as you can see, since we have 2 to the power n, z by 2 to the power n z, 2 is not an odd prime, hence this becomes false. Now there is this way that you can also solve this problem. You can also solve this problem in this way as well, to use this proposition. You can use this proposition as well, that if you take z by 2 to the power n z, where n is strictly greater than equals to 2, and you are taking their group of units. So this will always be isomorphic to z2 cross z by e to the power n minus 2 z, which will never be cyclic. Okay, so these are the, so this is one of the counter examples that you can actually form, or that you can actually give to show that our problem is false. So the Gauss's theorem is something that you for absolutely need to solve this problem. Okay, so the moment you have Gauss's theorem, all the problems or the solution is kind of handed to you in the class. Okay, so this is all for today. We will meet with another session in the upcoming days. Thank you for joining.